This lesson is about standard unit vectors, and we talked about unit vectors in the last lesson as being just a vector that has a magnitude of 1. So now we're going to talk about a standard unit vector in terms of I and j being positioned along the x and the y axis. So they are defined as 1, 0 and 0, 1. So basically, when you look at this, I is the horizontal component and j is the vertical component. So we can take any unit vector and we can write it in the form AI plus BJ. A being the horizontal component and B being the vertical component. So when you talk about it in terms of standard unit vectors, we are going to incorporate I and j, which is just verifying and validating that we have our correct horizontal and vertical components. So this is called a linear combination of vectors I and j. And the following steps, you can use the following steps to prove that these are equal. So what I'm going to do is I'm going to rewrite this as the sum of two vectors. So I can write this as A0 plus 0B, because A plus 0 is still A and 0 plus B is still B. So I can write that as a vector addition problem. I can factor out the A from the first one, and that gives me 1, 0. I can factor out a B from the second one, and that gives me 0, 1. And then I can substitute I in for 1, 0 by definition, and j in for 0, 1. So AI plus BJ. So these are your linear combinations that incorporate the vertical and horizontal components to it. So if you are going to rewrite this vector in terms of a linear combination, it does come out of the arrows, the component vector notation, and it just becomes 2i plus 5j. In number 2, we get negative 7i plus 3j. Now, in number 3, we have to create the component vector first before we can write the linear combination. So if you recall from the last one, we're going to add our x, or we're going to do our x2 minus x1 and y2 minus y1. So that would be negative 9. I did that backwards. I apologize. I apologize. My component. I had that right. I apologize. I doubted myself. So to do the component vector, we're going to do x2 minus x1. I had it right. I doubted myself there for a moment. All right, so here's x1, y1, x2, y2. So the component vector for rs would be negative 5 plus 9, because minus a negative is a positive. And then we're going to do negative 6 minus 8. Now that gives me the component vector of 4, negative 14. The linear combination would be for I minus 14j. And that is the linear combination in terms of I and j. Now, we're going to do the same thing with number 4. So I've got to find the component vector first. So here's x1, y1, x2, y2. So that would be negative 2 plus 10, 5 minus 6. So my component vector would be 8, negative 1. My linear combination would be 8i minus j, understood to be a 1 right there. Okay. Any questions about any of that, please let me know. Trig forms of a unit vector. When you start getting into a unit vector, you are starting, you're going back to the unit circle. So if U is a unit vector and the terminal point of U lies on the unit circle, okay, so make sure you have your unit circles because we will be able to use that. So this is what they're talking about if you've got a unit vector. Basically, that's the radius of the circle. Therefore, when you have U equals to the component vector AB, it can be written as U equals to cosine of the angle, sine of the angle. Okay? And as a linear combination, that would be cosine theta I plus sine theta j. Right? Because remember, if you remember, every xy ordered pair is cosine first, sine second. So your A and your B, your A corresponds to cosine, your B corresponds, the second element corresponds to sine. And then, of course, you can write your linear combination in terms of your trig functions, which is great. Now, because every vector is the product of its magnitude and its corresponding unit vector, we can write vector V in the following forms. We can take V and we can take the magnitude times the vector's unit vector, and we can end up with the magnitude of V times cosine theta, not plus, cosine theta, sine theta. This also gives us the option to do the magnitude. You can distribute, because that is a scalar. The magnitude is a number, so it is a scalar. And you can multiply it into the component vector. And then you can take this answer and write it as a linear combination of the magnitude cosine theta I plus the magnitude of sine theta j. So lots of things going on in this particular lesson, but we're taking what we know. We're taking our component vectors, we're writing them in linear combinations by adding the addition to the horizontal and the vertical components I and j. And then we are also translating that using our unit circle trig functions. So if we need to find the component vector for each of the vectors with the given magnitude and direction, they've given us the magnitude, which is great. They've given us the angle, which is great. So if I want to find the vector, the component form of the vector, not the linear combination, just the component form, because you can take every component form and turn it into linear by just adding the i's and the j's. So this vector would be 8 cosine 60, 8 sine 60 degrees. This is the last variation that we used up here. I apologize here because we're not doing linear combinations. We're just doing the composite. And then the next thing I would do is I would identify what cosine and sine are at 60 degrees. So that would be 8 times 1/2. and 8 times square root 3 over 2. And that gives me the final component vector of 4 square roots of 3. To do number 20, we're going to do very much the same thing, just to plug and chug and pull values off of your unit circle. So the vector, the component vector that has this magnitude and this direction will be 20 times cosine at 225 degrees, 20 sine at 225 degrees. Now, we have to go to our unit circle, and we're going to replace sine at 225 and cosine at 225 with their values. Those are both negative square roots of 2 over 2. And then I end up with the final component vector of negative 10 square roots of 2 and negative 10 square roots of 2. That is my component vector that has the magnitude of 20, and it has the directional angle of theta. Now, if you were to take this and go backwards, you would go right back to the 20, what we did in an earlier lesson. And if you did the tangent of B over A, you would go right back to your theta. You might have to tweak it a little bit to get that third quadrant angle, but it can be done. All right, the next two problems are basically the same thing. So we want vector, I apologize up here, I did not use the right, we're doing vector V or W, not V. So here I'm going to do vector K. My component vector would be 12 cosine 150 and 12 sine 150. That's going to get me 12 times negative square root 3 over 2. That's the value of cosine at 150 degrees. And then I'm going to get 12 times positive 1/2. And then when I simplify that, I get negative 6 square roots of 3 and 6. That is the component vector that has this magnitude and that directional angle. Last one of these, I am going to take my magnitude multiplied by cosine of 340 and sine, or forgot my magnitude, multiply my magnitude by sine of 340. Now, the difference here is I cannot give them an exact value because sine at 340 is not a unit circle angle. So you are probably going to be given the option of rounding. So if you put your calculator in degree mode, always check, make sure you're in the correct mode. If you multiply 30 times cosine of 340 degrees, you should get 28.19. And then when you do 30 times sine at 340, you should get negative 10.26. All right, so sometimes exact, sometimes rounded. So be careful. Make sure you pay attention to what MathXL is asking you for. All right. So now we are going to write each vector in trig form. And what that means is we are going to end up with a vector that equals to the magnitude of cosine theta times the magnitude of sine theta. So we have a lot of work to do because we were given a vector and now we're going to have to find the magnitude, we're going to have to find the directional angle, and then we're going to plug that information in. So the first thing I need is I need to do the magnitude of V, which would be square root of 15 squared plus 8 squared, which gives me square root of 289, which is 17. Second thing I need to do is I need to find my directional angle, and that's tangent theta equaling to B over A. Now, You do have to pay attention to your quadrant. You're in quadrant 1, so as long as when I do the inverse tangent of b over a to get theta, that my answer is a first quadrant value. So when I do inverse tangent of 8 over 15, I do get a first quadrant angle, which is 28.07 degrees. Now, I'm going to write my vector in trig form. So my vector in trig form is going to be 28.07. I'm sorry, that's my angle. Magnitude first. Magnitude is 17 times cosine of your angle, and magnitude times sine of your angle. Now, do not actually multiply that out because that gives you 2 decimals and you are removing the trig function. So they want it in this format, or if you would like, you can put the 17 out in front and just not multiply it into the component vector. Okay, so one or the other should be fine. Now, we're going to do the same thing for the next few examples. And so here, I'm going to find the magnitude of m. So that is going to be the square root of negative 3 square roots of 2 squared plus negative square roots of 6 squared. And when you do all of that math, you get the square root of 24. And that simplifies to 2 square roots of 6. Now, I am going to find my directional angle, which is b over a. Since this is a quadrant 3 angle, I'm probably going to have to do a little finagling, because when I do this original, when I find my original value, it is not going to be a quadrant 3 angle. So I'm going to take inverse tangent of negative square root 6, divide that by negative 3 square roots of 2. And when you do this initially, I apologize, my calculator turned off. So I get inverse tangent of negative square root 6 divided by negative 3 square root 2. And that gives me a theta that is 49.11. Now, I can't use 49.11, so I am going to actually have to, wait a second, I must not have calculated something right. I apologize, I did not type that into my calculator right. When I do this, I should get 30 degrees. Now, 30 degrees clearly is not a third quadrant angle. So remember, I have to come over here and I have to go 30 degrees away. If I'm in the right quadrant, I'm going to go 30 degrees into the third quadrant. So that would be 180 plus 30, which would give me a 210 degree angle theta. So the theta that I need, the directional angle in quadrant 3, is 210. 30 is not in 210 or in quadrant 3, but I had to use it. So you can do one of two things. You can put your magnitude, which is 2 square roots of 6, out in front. And you can write cosine 210, sine 210, or you can multiply by that scalar and have 2 square roots of 6 I'm not really sure, to be honest with you, which one Math Excel is going to want. So if you type in one and it tells you that is incorrect, I would try the other version. So if you type in the first one and it tells you no, then go ahead and use that 2 square roots of 6 as a scalar. Now, for 11 and 12, they're adding even more work to our plate. Well, actually, they're not adding more work to our plate, but you have to realize that this is the vector -1, 7. If you take out the linear, if you can go from a component vector into a linear combination, you can shortly go backwards. So the magnitude of P is square root of -1 squared plus 7 squared. That is the square root of 50, which is 5 square roots of 2. Now, I need to find my directional angle. If you want to, just go ahead, instead of writing that down every time, you know that theta is going to be inverse tangent of b over a. So my b value is 7 over -1. So when I do inverse tangent, you are in quadrant 2. So you probably are going to have to do a little bit of finagling. So inverse tangent of -7. That gives me 81, -81.86. Now, I need a second quadrant angle. So I'm going to come over here and I'm going to backtrack 81.86 degrees. So basically, 180 minus 81.86 will give me the second quadrant angle theta that I need. So 180 minus that answer. I apologize. 180 minus, I did a minus a negative, which did not work out too well for Ms. Chapman. 98.13. That is our directional angle that we are going to use. That angle does fall in quadrant 2. So you have two options. You can put the 5 square roots of 2 out in front of your trig vector, 93.18 sine 93.18, or you can put it inside. Does not matter, because eventually you'll have to do one or the other. And like I said, I do not know which variation that Math Excel is going to want. So when I do R, I'm going to think about its component vector, -2, 2. I need to find my magnitude first, which is, apologize, magnitude first, which is square root of -2 squared plus 2 squared, which is square root 8, and that is 2 square roots of 2. Then I need to find the inverse tangent of b over a, so 2 over -2. So basically you're finding the angle that goes with inverse tangent of -1. So inverse tangent of -1, that is a -45-degree angle. Now, this vector is in quadrant 2. So I'm going to have to come over here and do like I did before. I'm going to take 180 and I'm going to subtract 45, and that gives me my second quadrant value of 135. And so I can write my trig vector with 2 square roots of 2 on the outside, cosine 135, and sine 135, or you can scalar multiply and put your 2 square roots of 2 inside as your multiplier. I said it and I didn't do it. 2 square roots of 2, sine at 135. Now, number 13 is even going to add more work for us to do because I have to find the component vector first. So the component vector that goes with AB, that component vector will be -8, -4. We did that earlier. -9 minus -1, x2 minus x1, y2 minus y1. So we did that earlier. I can find the magnitude of vector AB, square root of -8 squared, -4 squared. That gives me the square root of 80, which is 4 square roots of 5. This vector is in quadrant 3, so we are going to have to do a little finagling because our directional angle has to be between 180 and 270, so we're going to have to figure that out. So when I do my inverse tangent of b over a, so -4 over -8, so if you want to just type in 1/2, that's fine. When you get inverse tangent of 1/2, you get 26.57 degrees. Clearly not a first quadrant angle. I need a third quadrant. So this time I'm going to rotate into third quadrant, 26.57 degrees. So I will take 180 and I will add 26.57. And that will give me a third quadrant angle of 206.56, or 57, I should say. Now, my component vector for AB, or my trig vector, I should say, you can put 4 square roots of 5 out in front, and we have cosine of 206.57. Sine 206.57. And I apologize, I'm not using the appropriate symbols. That should be component. Or you can put the 4 square roots of 5 on the inside as its scalar multiplier. All right, and the last example for today, for this lesson, we're going to have to do the same thing. I need the component vector for yz. So x2 minus x1 gives me 2. y2 minus y1 gives me -6. That puts me in quadrant 4. So I need a positive quadrant 4 angle. So the magnitude of vector yz is the square root of 2 squared plus -6 squared. That gives me the square root of 40, which is 2 square roots of 10. Then I need to find my directional angle, which would be inverse tangent of -6 over 2, which is basically -3. That's probably easier to type in. So inverse tangent of -3, that gives me -71.57. So what I'm going to do here is, instead of going into third quadrant, I need to be in fourth quadrant. So I'm going to go -71.57 degrees. But I need the positive. So this time I'm simply going to take 360, subtract the 71.57, and that will give me a fourth quadrant angle of 288.43. Now, to write your final YZ vector in trig form, that would be, I apologize, we can put our 2 square roots of 10 out in front, and we can do cosine 288.43 sine 288.43, or you can do that as a scalar multiplier and put the 2 square roots of 10 with both trig functions inside the component vector. I know that's a lot of work, but when we start solving some of the application problems that are coming our way, we need the practice with this stuff. So if you have any questions, please feel free to contact me.